Hi everybody, welcome back to the final recording for this topic, and it's on antibacterials and antifungals. Now in the next few slides there's lots of text and diagrams and everything, so I'm just going to pop in to the back here. Drugs and antibiotics do display this selective toxicity, which is great for us. And what does selective toxicity means? It means that the drugs cause greater harm to the microorganisms than they do to the human host. And they do this by generally interfering with biological structures or biochemical processes that are common to sort of all bacteria but not to humans. For example, some antibiotics target the bacterial cell wall, right? And our cells in our bodies don't have this cell wall consisting of peptidoglycan. Remember as well, toxicity of drug is expressed as the therapeutic index, and it is the lowest dose that's toxic to a patient divided by the dose typically used for treatment. And drugs with a high therapeutic index or a wide therapeutic index are far less toxic to a patient. So in general, if you want to design a great drug to use, it would display a high therapeutic index, but unfortunately not all drugs do have this high therapeutic index. Antimicrobial drugs in general sort of display two types of antimicrobial action. So antibiotics that work against bacteria may either kill bacteria, and in this case they're called bactericidal, or sometimes the antibiotics just inhibit the growth of the bacteria and sort of halt it. So that's why they're called static. So they have a bacteriostatic effect. And bacteriostatic drugs rely on the host immunity to eliminate the pathogen. So by halting the growth of the pathogen, that then, allows a reduction in growth and the immune system then to eliminate the pathogen. And bactericidal drugs are useful in situations where host defenses can't be relied upon to control the pathogen. So if the pathogen is very virulent, you might need to use one of these bactericidal drugs. Antimicrobial drugs also have a spectrum of activity. And so they do sort of, they vary with respect to the range of organisms that are controlled. Some antimicrobials have a narrow spectrum. What does that mean? It means they work on a narrow range of organisms. So say, for example, just gram-positive organisms only or gram-negative organisms only. Then we have the ones that have a broad spectrum of activity, and they, as their name suggests, work on a broad range of organisms. So they will both either be, cidal or static to gram-positive and gram-negative bacteria. However, that might sound really good, and they have sort of a wider range of effect on pathogenic organisms, but the disadvantage of broad spectrum antibiotics is that they do disrupt the normal flora in the body as well. Other features of antimicrobial drugs is sort of in the area of pharmacokinetics, and drugs are differ in how they are distributed in the blood, how they're metabolized, and how they're excreted. And this is a very important factor for consideration when prescribing these drugs. Remember that the rate of elimination of a drug from the body is expressed as the half-life, so the time it takes for the concentration of a particular drug to decrease in plasma by half. And the half-life itself then dictates the frequency of dosage. And remember that patients with liver or kidney damage will tend to excrete drugs more slowly. So this liver and kidney impairment will extend the half-life of particular drugs. And in terms of antimicrobials, this is a really important factor to consider. Sometimes as well, antimicrobials need to be given in combination to treat some infections. One antimicrobial might enhance the effect of another antimicrobial, and of course that would be a synergistic interaction. And sometimes, the effect is not synergistic, but it's literally just an additive effect where the sum of the two drugs is sort of equal to the sum of the effect of each of the drugs. And we do know, of course, that we have, if one drug interferes with another, the effect is antagonistic. That probably wouldn't be very beneficial in terms of, administering antimicrobial drugs, though. As with sort of all medications, there are adverse effects. And with these antimicrobial ones, some of them are very serious. And if they do occur, they are life-threatening. So some people do develop hypersensitivity, allergic reaction to antimicrobials such as penicillin. And this is a life-threatening one, which can end up, with the person having or going into anaphylactic shock. Again, just like every sort of allergic reaction, the first time the person is given penicillin, their immune system is sensitized. Remember, with these immediate hypersensitivity reactions, we're talking about preformed IgE antibody, so that then on subsequent exposure to that penicillin, the antibodies are already made. So there's an immediate hypersensitivity reaction causing systemic vasodilation and hypertension and decrease in blood pressure, and then organ systems go into shock. There are also toxic effects of antimicrobials. One of the most serious ones is aplastic anemia, where the bone marrow can't make red blood cells or white blood cells. Antibiotics as well can suppress normal flora, and this can sort of result in antibiotic-associated colitis, where toxic organisms are given the opportunity to establish themselves. So what does that mean? If somebody's given sort of a broad spectrum prescription of antibiotics, going to work against the pathogenic organisms, but also will wipe out the normal flora, particularly in the gut. And in that case, then a toxic organism such as Clostridium difficile is then given the opportunity to establish itself in the colon, for example. And Clostridium difficile is very difficult to remove once it colonizes the colon. And of course, antimicrobial drugs can develop this these microorganisms can develop antimicrobial resistance as well. And many microorganisms do have an innate or adaptive resistance to antibiotics. And I'll talk about antimicrobial resistance in more detail. Firstly, though, looking at the mechanisms of action of antibacterial or antibiotics, and this does sort of vary depending on the class of antibiotics. So some classes inhibit cell wall synthesis. These include the beta-lactam drugs, the penicillins, the vancomycin, and another antibiotic called bacitracin. And how these work, and you probably don't need to remember this information, is these antibiotics will inhibit the cross-linking of the NAG and NAM molecules of peptidoglycan. Remember, peptidoglycan being that important sort of polysaccharide in the cell wall. So by doing that, they inhibit cell wall synthesis. We also have other classes that inhibit protein synthesis. You can see lots of those there. Again, you don't need to remember those, but maybe some of you have had to take a macrolide at some stage or a tetracycline for an infection. Inhibition of nucleic acid synthesis as well. Inhibition of metabolic pathways is another way they work, and interference with cell membrane integrity is also a mechanism of action. So now looking at the actual mechanisms of resistance. So some organisms can produce enzymes that chemically modify a drug. And a good example of this is microorganisms can produce this enzyme called penicillinase that breaks the beta-lactam ring of penicillin antibiotics. So if it breaks the beta-lactam ring, then the penicillin antibiotics is no longer going to be able to, exert its antimicrobial effect. Alteration of target molecules is another one, where minor structural changes in the antibiotic target can prevent binding. So changes in ribosomal RNA prevent, that should say the macrolides, not the macrolides, from binding to ribosomal units. Again, you don't need to remember, the details of this slide. But if you look over here, you can see sort of this pattern of resistance developing here. So here we have all of these antibiotic sensitive microorganisms. The antimicrobial drug is added and the sensitive organisms are killed or inhibited, but you can see that resistant survivors can multiply without competition. And then once they start multiplying, all of the progeny from the multiplications are going to be resistant. Okay, so what you have to imagine is, my bacteria replicate very, very quickly. And so within this population of all of these sensitive bacteria, most of them are killed, but even if sort of one becomes resistant, then it can multiply without competition to produce all of these antibiotic resistant daughter cells. Other mechanisms then of resistance include decreased uptake of the drug. So there might be, alterations in the porin proteins of the microbe, which decrease the permeability of cells. So you can see these porin proteins prevent entry into the cell, and so prevent, I should say, drugs from entering the cell, and therefore they're going to have less of an effect, right? Also, you can have increased elimination of the drugs. So some microorganisms produce these efflux pumps, and that increases the overall capacity of the organism to eliminate the drug. So here you can see we have a sensitive cell or a non-resistant microbe. You can see we have our drug. The drug enters and it binds to a particular target, and it's going to, kill that microbe, right? Or halt its growth or something. Okay, we have here though some microbes that have these efflux pumps. So pretty much the drug sort of enters, but the efflux pump of the bacteria pumps it straight back out again. Okay, so this will allow the organism to resist higher concentrations of drugs. An example of that is some microbes develop their resistance to tetracycline in this way. And you can see these other two here where there's an alteration in the target molecule, so the drug can't bind to the target any longer, and also these drug inactivating enzymes that I mentioned on the previous slide, where the microorganism produces an enzyme that modifies the drug and therefore inactivates it. There are two ways that microbes sort of acquire resistance, right? So it can be due to spontaneous mutation, where there's alteration of existing genes. So you can see a spontaneous mutation here occurring in the bacterial genome. And that will then sort of confer resistance on that bacterium. And if you follow that one down, you can see then that it can, replicate without competition. And this is called vertical evolution. The other way is via horizontal evolution, and this is where a bacterium acquires new genes. And this resistance is acquired by transfer of new genes called horizontal transfer, as I mentioned. So if you look here, we have this bacterium here, and it's got this coiled genome here, but we also have this sort of extra bit of plasmid DNA here, and that plasmid DNA often contains often confers antibiotic resistance. Okay, so this little bacterium here can then sort of transfer that plasmid to all of these, and that will then confer antibiotic resistance to them, as you can see there by that R and that acquisition of that sort of extra chromosomal DNA there. This little schematic might help to explain it a bit better in terms of exposure of bacteria to antibiotics. Here you can see a bacterial population. None of them have resistance to antibiotic X, so they all die. So they all get wiped out in the presence of that antibiotic. Here, though, we can see a proportion of the bacterial population gains resistance to antibiotic X via mutation. So some bacteria with resistance, you can see this one here, survive. Most of them are killed, but this one has the resistance, so it survives, and then it multiplies, passing on that resistant trait, and what you end up then is with a resistant bacterial population surviving subsequent encounters with the antibiotic X, so it no longer works. Okay, here we have the plasmid bit. Some bacteria can gain resistance via acquiring genes from external sources through sort of any of the following means. Now, we haven't gone through it here. Transformation, transduction, conjugation. Again, through the acquiring of those genes, some of them will gain resistance, and then they can multiply, and then the population survives further encounters with antibiotic X. So yeah, it's just different ways of acquiring that resistance, either by spontaneous mutation or through this sort of extra chromosomal DNA. Very last slide of this topic is looking at the treatment of superficial mycoses. So here we're talking about obviously fungal infections. There are lots of antifungal agents. Some are given, as a tincture, others via a cream, oral administration for antifungals also is done, particularly if somebody has a systemic fungal infection. But here we're talking about, and those drugs, right, are really powerful drugs. They tend to have lots of interactions with other drugs, and they have lots of side effects or adverse effects because of the fact that, fungi are eukaryotic like our cells. However, here we're talking about superficial mycoses. Cyclopirox is an antifungal agent. It's a synthetic antimycotic drug. Its mechanism of action is poorly understood. However, we do know that it's a chelating agent, forming chelating complexes with things like the iron and the aluminium ion. And so some fungal enzyme systems to be operational are dependent on the iron and aluminium ion. So that's how it works in that way. Some of these drugs are fungistatic, others are fungicidal to other, just depends on what the fungal infection is. And they also have an anti-inflammatory effect also. Cyclopirox is usually well tolerated, so it doesn't have that many adverse effects, can cause itchiness and burning sensation at the site of administration. Now, there are lots of other sort of treatments that you can use. Whitfield's ointment is one of the oldest ones. And then we have these brand names for Loceral and also Dactarin, which are particularly used in tinctures and creams. All right, everybody, that's it for the immune system. I hope that you've really enjoyed learning about different immune disorders and how we treat them. And it's really sort of piqued your curiosity to find out more.